Why don't we get started? I guess today's the last day, right? So get started. This is the home stretch, the home track, or the home stretch.
I think
so
the home run.
The home. This is the home stretch. This is the home run. So Sherry Lee will be telling us. She's just up the hill, and will telling us about using randomized algorithms and various sort of scientific computing type problems in certain constructions of, I guess, HSS operators.
Okay, great. Thank you. Can everybody hear okay? So I'm up the hill, very local, and I have several collaborators work on this, very good. And in particular, for this particular talk is Chris Gorman. He's still finishing PhD from Santa Barbara, and he came with us for 2 summers, worked quite a bit on this. So also did quite a bit of theoretical work, which I want to show. But also we want to, for this conference, I want to talk to people and get some advice in terms of using randomization. We just started doing this recently. And the majority of the work currently is funded by DOE exascale computing project. And if you don't know, DOE is planning to have the exascale machine available either end of 2020, 21. So in that 2-3 years. And obviously, a lot of investment needs to be, looking at hardware, software, etc. But one important component is the scalable algorithm. That's where, we fit here, and all these randomization algorithms. It's a very, very good. So the talk is mainly about hierarchical matrix, and its mathematical foundation is very similar to fast multipole FMM, discovered more than 30 years ago. And in the FMM term, you are talking about the particles. So you talk about a near field, far field. Far field, you can do some aggregation, approximation. But if you put this in the matrix form, you're talking about diagonal, close to diagonal, which is a near field, and then off diagonal, far away, which is the far field. So it's a very similar kind of concept. So in the matrix form, on the right side, this figure here for the off diagonal block, and very often you can, even though it looks dense, but you can use some low rank approximation to approximate it very well. So once you put it into the algebraic matrix form, it's actually very powerful. You can do matrix multiplication, of course, you can do factorization, you can do inversion. So that's where the power comes. And then the field, the hierarchical matrix in recent years have been very active area. So people invented different formats and do the different operations. So here I just give you 2 examples. One is on the left is the H matrix was invented almost 20 years ago by Hackbush, their group. So here you do hierarchical partitioning. The diagonal block, you keep it as dense since they cannot be approximated well. But then you look at the off-diagonal block. Depending on your matrix, you have the flexibility whether you want to do the compressed representation. Here, this one, if it doesn't allow you to compress, then you represent as a dense block, but then the green ones, you can compress. So it's a very flexible format. But then on the other hand, if you want to do the matrix factorization with this format, it's not so easy. It's actually more expensive. On the right side here is the hierarchical HSS. It's the hierarchical semi-separable matrix. It's discovered more recently, but almost I think more than 10 years now. Was started here. Minggu was involved very much, and then his former student Jianlin Xia. Right now, he's still actively working on this. So this one has a slightly nicer structure. So you still have a hierarchical partition, and then the blocks. You look at the block organized off-diagonal block organized in a hierarchical way, and also you organize your bases. You can compute in a hierarchical nested basis. So in this slightly better structured way, you actually can do the factorization inversion. It's much faster than this. So I'll show you some result. Okay, about this HSS. It's really starting, you have to do the partitioning. So in the Hackbush, their term, they use block cluster tree, block cluster tree. So in the matrix term, you say, for example, you decide to the bottom level, like a block size 100 or something. And then this is your bottom level diagonal block. The off diagonal block, you do something, and then every time you merge, pairwise merge of the off diagonal block. So pairwise merge into the next level of diagonal block. So then you get this cluster tree. When the cluster tree is organized, when you do this partition both row-wise and column-wise, then it's the block cluster tree. So this tree is sidewise, okay. And then the HSS, one thing is to look at this off-diagonal block in a nested way. So here, for example, this is your bottom level off-diagonal block. You did the SVD type of compression, the U1, U2 here, right? And then when you move to merge into the next level, you can compute this SVD again from scratch. But that doesn't save you a lot of work. So what in this case you do is that you use what you have already computed from the two children here. And at the parent, you only need to get a small this orthogonal basis, the representation. When you multiply them out, it's the mathematical way as the true representation. So you can multiply them out as a big U vector. But you can see that with this, you actually save storage, also save operation. But then everything, when you do operation, you need to follow this HSS tree to do the sweep from bottom to up and top to bottom. So that's the HSS in a nutshell. And as I said, you can do factorization. And because in HSS we have a lot of these unitary matrices, so we do a lot of little uniform transformation to transform into the L matrix. And in particular here, we call this ULV factorization. So this is your A matrix already compressed in HSS, right? And then you do all these little orthogonal transformation and some permutation here. And in the end, that turns into this L matrix. So once you have this factorization, the orthogonal matrix and L, then you can do the solve. So that's the factorization. Okay, so what I really want to get into is this the compression kernel, which is critical for all these hierarchical low rank approximation. And only recently we started looking at using randomization. Before, our first version of the code was using traditional rank revealing QR. And it turns out to be not so great for, it's actually very difficult to do when we embed this scheme into the sparse direct solver, like a multifrontal solver. So then essentially we have to redo, redo a lot of the software. And this randomized sampling is very familiar to all of you. I think that's what this workshop is about. So I will do very quickly. And so essentially for any matrix A, suppose you know the target rank, and then you take this random matrix omega with slightly oversampling the column dimension, and then multiply, get this sample matrix. You get this Q is the orthogonal basis of this sample matrix, and turns out this Q will be a good approximation of the column basis of A matrix. Okay, and then Joe is here. It's good. This is a very good SciM review paper. A lot of different aspects about randomization applied to numerical linear algebra, so it's highly recommended for reading. So in this paper, if you read paper, you can see that there are different ways to quantify this approximation quality. So for example, on average, expected value of this is given by this quantity. This just says that if you do SVD for A, for example, you just take the leading k singular vectors, then your approximation is the best, which is the next singular value. But with this randomized sampling, then you get something slightly worse than the optimal. But then the factor is not so big. It's related to the matrix dimension. And the probabilistic way, you can say that with very high probability related to P, that's why this P doesn't need to be very big. with high probability, then you get error bound is bounded by this. So that's a very nice tool. And the nice thing about this sampling is you can build the solver actually is matrix free, because all we need is to get the sample matrix multiply here. We don't need to access matrix essentially. So that's a very nice thing, very useful for many applications. And another thing I alluded already, it's very good for embedding this in sparse frontal solver, simplify a lot of things.
Excuse me, Sherry, what does the rank revealing QR get you as opposed to just a plain QR?
Rank revealing QR give you something like approximate this guy.
So do you use a strong one or just?
We didn't try the strong one. Strong one could give you, I think, a better bound. More guarantee. We used only the column pivoting one.
Already.
That works already. Yeah. Okay. So then to do this RS. Put in the context of to do HSS compression is basically you can think about you have a pre-processing step, which is the sampling. Let's say suppose your matrix is non-symmetric, and what you do is you need to sample both the column space and also the row space, the transpose. You multiply them together. This is a separate pre-processing step. And then because we are only doing the compression for the off-diagonal block, so for each of these sample matrix, it's represented in this way. So you have to subtract the diagonal block in order to get this the Hankel block, which is the off-diagonal one. So it's just a little bit of manipulation when you go do the compression along the HSS tree. Okay. So the practical issues is actually we get the code, but then there are a lot of problems when we give the people to use the software. So one is we don't know the rank, and we want an epsilon rank. People usually want a certain tolerance, right? The error. And then sometimes in the internal blocks, the singular spectrum may not be decay as you like. And sampling is expensive. So I will mention some of our solution for these issues. So the first solution is we want to get this adaptive sampling. But adaptive sampling, it's easy to say, but then the question is you need a good error estimation to stop your adaptation. And that's something Chris Gorman did a lot of work. And then sampling, there's if you just do the matrix multiplication, it's order n-square operation. It doesn't, it's very expensive. So there are some tricks. And in fact, I want to talk to people about this. So adaptive sampling is you start with, S1, for example. You say, I don't know the rank, right? I will start with 100. Then every time I increment. So when you do this S1, do the QR to get the basis. And then when your error is still large, then you add more samples to put into this space. But you need to do orthogonalization within this the new Q, and orthogonalize it against the previous one. So the procedure is very simple. The question is, what's the error? So remember in the HSS case, what we do is we do the sampling beforehand. So you already have this sample matrix. And then you do compression along the HSS tree, right? So the issue is you don't know whether the samples are enough, but you discovered, in the middle of this tree, that means in the middle, one of the, off-diagonal block here, you discovered that these number of samples you use is not enough. And one way to overcome this problem is you say, I scratch everything, I add more samples, start from scratch. But that means these guys, they are already good, that work is lost. So it's not very good. So what we do is at this node, this is a partially compressed node, all the nodes below that are already compressed. We don't want to redo this compression. So what we do here is we try to expand spaces, the samples only at this node. Okay. So the one question is here we don't have the matrix A. We only have the sample matrix. And then we need to stop this adaptation, having some good stopping criteria. So we need to establish a certain kind of relationship between the error, between the A norm and the sample matrix norm. And that's, could be actually derived very easily from this relation. So if you write your matrix A in the singular value case, suppose you drop those, and then you have defined another variable C, which is the V transpose times X. Then the C is also a Gaussian random vector. So here my X is from a normal distribution Gaussian. So then AX, the two norm, can be written in this way. So it's just the sum of the singular values, the square plus this C square. Okay. So this C is actually just the chi-square with the mean is 1, the chi-square degree 1. So then you can write down this expected value of this AX2 norm is just the sigma 1 square plus this, because the expected value of C is 1. So then that's related to the A norm of the Frobenius norm. So you can see that with this sample matrix, sample vector, the norm is related to the matrix A itself. So that's the relation we need in order to stop the adaptation. And if you have D sample vectors, then your expected value is just D times this guy. Okay. So then with this, we can have a good stopping criteria. So when you expand into the new S2 here, and what you do is you look at the sample, the F norm of this in the absolute case, just divided by square root of D. If this one is smaller than that, and this will be approximately smaller than that. And similarly, you can use this sample, S2, this new sample, to do the relative criteria. And the cost is very small. It's just one reduction of the sample vector norm. Okay, so there's some technical details here. So we did experiment with this using this parameterized matrix. So here in this matrix, I have UV, they are orthogonal matrices with a predefined rank. Okay, and then D diagonal is actually control how the singular values are decayed. So in this case, it's decay very nicely relative to this rank R. And the experiment I did here is for the row dimension. Here, I'm changing the accuracy, the tolerance from large to small. And for the column dimension, I'm changing the relative tolerance. So we have two tolerances. So this example is initial D, the random vector is 16. Every time we add 16. So we just keep adapting. So then in table, each entry I have two values. One is the computed HSS rank. Another one is random samples used. So as you can see that with this very nice matrix, well decayed, then your computed random, the vectors you use actually never exceed the actual rank. So it's usually very nice, even when you ask for very high accuracy.
So computed intelligently, does that mean you're using twice as enough in the last?
Oh yeah, that's a very good point. Yes, we do twice, actually. Yeah, that's similar to the twice is enough, but that's a very good point. And then we change this parameterized matrix so that diagonal is 1. There's no clear decay, and the same experiments. But then you can see that the only difference, everything, if you don't ask for very high accuracy, everything is still works very well, except at the lower right corner here. When you ask for very, very high accuracy, then the code needs to compute a lot more samples in order to get that level. But that's really is, very, the case that you really need to want very high accuracy. So then for this same parameterized matrix, it's a bit larger. I'm giving you just want to see some computational cost of adaptivity. So the dimension is 60,000, and then it has a decay of the singular values, and then this is run on the 1,000 processes. So in the table here, the experiment is we're starting with 128, the random samples. The increment is 64. In the table, I gave you 3 columns of the time and the rank, etc. So the first column is, since for this matrix I know the rank, so we give precisely the number of samples. This is the fastest possible. The middle one is our adaptivity. Then the last one is, suppose you don't have this adaptive strategy, then you can, as I said before, you can go back, scratch everything and then add sample, redo everything. So you can see that the compression, in this case, we did adaptation 17 times. And for the hard restart, this experiment, there's 4, okay. So you can see that even with the 17 times adaptation, the time is not so much more. It's just slightly more than the fastest possible. And it's much, much faster than if you restart from scratch. Okay, so let's see the one last thing I want to mention is this sampling. Sampling is the pre-processing. So in fact, for a lot of cases, if you just do the matrix vector multiplication to do the sampling, it's actually very expensive. So the sampling cost dominates. So it's like order of R, n squared R is if it's the target rank. And in practice, it can be 80% of the runtime. So that's not very good. And there are some ways to do this. You can use some structured matrix, for example, Hadamard matrix, FFT, or if the matrix is tuplets, you can do FFT, or you can do some. So those things we haven't tried. But what we have tried is to use the H matrix format to help sampling. So I'll give you one example here. So this is the example of using kernel ridge regression to do the classification in the data science. So the kernel matrix we're using is the Gaussian matrix, and if you know the kernel regression method, so internally you need to solve when you build the model to do the training, you need to solve this linear system K plus regularized term. And here we use our fast HSS H matrix technique to do this. So what I want to show you is here I have 2 data sets from UCI. One is SUSY, is 4.5 million. The dimension feature space is 8, so it's relatively easy. It's a low dimension problem. And another one is a COV type. It's 500,000 the data points, and the dimension is higher, it's 54. Usually higher dimensional problems is harder. And in the experiments here, we did for the 2 data sets, we vary the number of processes. So one is 32 processes here, one is 512. So you can see that what we do here is we use H matrix, which is easier to construct, faster to construct. But even with the 512 processes, it takes still take 18 seconds, for construction. And then we use this approximate H matrix to do the sampling, then to help this HSS construction. So that's already faster than if you do the traditional matrix vector multiplication. But still, the sampling is still like 10 minutes compared to dominates everything else. So once you have the compression, then the ULV factorization and solve are pretty much instant, very, very fast. So there's still issue of how to, improve the speed of sampling. That's something, we still need to look into. So I'll just give you a couple of charts about scalability of the current solver. And this is the example, 2 examples. So one is from quantum chemistry. It's actually a tuplets matrix. The diagonal is defined like this, off diagonal is defined like that. It's constant tuplets. And another one is this parameterized matrix. So we run up to 4,000 cores. So for the quantum chemistry matrix, because the rank is small, it's like in under 100, the HSS rank. And then it gets very good scalability. But for this matrix, the rank is relatively big, so it scales worse. And we embedded this technology into the sparse multifrontal solver into all the dense frontal matrix. And this is the example of sparse scalability, up to 6,000 processes. So we have this sparse matrix dimension is 1.5 million. So in sparse matrix, usually there are different steps. There's a symbolic factorization, the numerical factorization, solution, etc. So the numerical factorization construction is relatively scaling well, but the other phases we still need to work on the strong scalability. Okay, and then this is just the pointer to the software. It's there's two components: a dense component, a sparse component. And the dense component you can represent either have an explicit matrix input, or if it's a matrix-free scenario, we have an interface for that also. And one thing I want to point out is really just for a lot of our papers, I didn't list them here, but if you go to the website, we have all the published papers there, so you can get them. So I think I'll stop here. This, after we introduce this randomized sampling, it helps a lot, but I think there's still a lot of things needs to be investigated in terms of numerics. And also, how to reduce the sampling cost is still a big issue. And then, because this kind of factorization is approximate, they work very well for elliptic PDE. But for some other applications, which at best, I think we can use this as a preconditioning. So we have some result for the preconditioning. And the nice thing about this, with this hierarchical way of tree structure, even in the sparse case, the multifrontal tree, then it's more parallelizable compared to traditional ILU, the preconditioning. And it's quite robust compared to ILU. It's good. So, but there are a lot of parallel computing issues. I listed them here. That's why we'll still continue working. Okay, thank you.
All right, any quick questions? And in parallel, do you want to see, to make sure that we get the next thing set up properly? So in parallel, because we want to make sure we have it.
In your
you
kernel
have a question or two.
Example, Sherry, does that mean you represented the kernel matrix as an HSS matrix?
Yes, that's right. Thank you.
Can I ask a quick question about for your machine, your like cup type and other kernel matrix things? How did you mentioned this question of like ordering? So what did you do? How did you do the ordering to make sure it had some reasonable hierarchical structure?
Yes. So with natural ordering, you can do hierarchical structure. It's our way is purely algebraic. But with so let me just take this.
But natural ordering, you mean like
just the data presented to us. And then recently we started using the KD tree, PCA, and recursive tuning to order, which improves
sure.
Improves the low roughness of the outlet.
But to like afford the KD tree, you project it all down to really low dimensions or something, or?
So we do the KD tree. It's still at higher dimension. You take up a dimension, you do the splitting for each recursively going down. And with that tree, we use that tree as our HSS tree.
I see, okay.
And similar for recursive tunings. So that's a separate paper.
Okay, cool.
All right, any other questions? All right, well, thanks again, Sherry.
You could, for sure. I think that or even Cairo. So, for example, graphical policy, just tone up the graphical policy, but you just tone up the
Machine or just the projector?
yeah, that's good enough.
Do you have your
option? You could do it or default. Yeah, I'm like doing some flags and supply. Potentially, and you say double. No, it's two general.